Okay, so can you see my screen now?
Yes, great.
Okay, thank you. So thank you, Bingshen, for the introduction. And also thank everyone to join our online workshop, especially for the ones in US. So I know this is not the best time for you guys to join, but yeah, really thanks. Okay, so yeah, due to the COVID-19 situation, now we cannot meet in person, but thanks to the Zoom platform, right now we're using,
Hey, hello.
the remote data centers, but we saw that we almost forget that it is supported by the infrastructures from data center. So what we are doing now in Xilinx, especially in Xilinx labs in Singapore, are to exploring the new opportunities in the data center infrastructures. More importantly, we are looking for the solutions, the architectures, algorithms, and all the ways we could make the infrastructure in data center more flexible and more efficient, right? So today, what I'm going to talk about is a new, some kind of new concept. We call it distributed adaptive computing, and this work is still ongoing, but we have some preliminary results. And I would also like to mention, the contribution from the team here in Singapore. So we have Joan, Yan, Henry, working with me, locally on this project in Singapore. And also we have, colleagues in Singapore like Gordon, who is also participating in this project. And also I would like to thank all the interns, right, in our lab to contribute to this project. Okay, so let me start the topic. So the first of all, as I mentioned, this is something, some work related to the data center. So as we all know, compute, storage, and the network are the three pillars of data centers infrastructure to support all kinds of different applications as well as services, right? And it is also well known that, the faster growing of big data is increasing the scalability challenges in supporting growing throughput, data speeds, and information complexity, which has led to a recognition on the limitation at the CPU-centric infrastructure traditionally. And this has been resulting in two major trends. The first trend, I would like to say within servers to offload compute from CPUs and move it to other parts of the server. For example, to specialized accelerators or placed closer to networking or storage. And also, Bingshen mentioned previously to place the accelerator or compute near or close to the data, right? So this is one trend. And the other, or the second trend across the servers is disaggregation of resources. For example, providing specialized computation servers or customized storage or networking applications over the network or spread in the data center, right? So this allows better scaling and also provisioning of resources to meet different application needs through customized composing, right? So and these two trends in fact can be seen in different contexts at different scales. It can be, within data centers, and it also can be across different data centers, right? Okay, so following these two trends, we propose the distributed adaptive computing, right? And which is a new network technology fundamentally. And it is, we try to propose a new technology based on our Xilinx recently defined silicon category, which is Adaptable Computing Acceleration Platform. We call it ACAP for short. And this addresses the challenges posed by the two major data center trends I just mentioned, which are offloading and disaggregation. And with distributed adaptive computing, right? So I may use DAC for short, right? So with it, in fact, DAC extends per server approach by custom hardware and software interconnection technologies between ACAP components to provide a uniquely flexible network solution to the big data challenges and scalable to address the ever increasing demands. And the figure on the left illustrates the broad DAC solution. So where disaggregated nodes are connected by an intelligent data center network, the example nodes show places where ACAP can be deployed. So and the node could have very different mix of accelerators, CPUs and SSD, something like that. So in this talk, I would like to briefly introduce two major places to deploy DAC technology. So as I listed them on the right, so the first place is the NIC location. So we propose the adaptable NIC, right, which is a kind of a new type of smart NIC. And also we could see it as a host network device. And further, we could also push the programmability or the flexibility from the host network to the intermediate network nodes. That is the second thing I would like to talk a little bit today. We call it adaptable switch. Okay, now let me just start from the adaptable NIC. So the existing NICs, right, can be classified into three types, as I listed on the right table. So the type 1 is the basic NIC, which provide the basic connectivity, right? And the second one, usually we call it a smart NIC or network acceleration, right? And a traditional way is to move some of the functions like OVS or crypto decrypto things or customer tunneling kind of functions, which mainly to handle the layer 2 or layer 2 below functions into the NIC side from CPU. And the type 3 NIC we mentioned to the ones that were adding more functions like machine learning, video transcoding kind of things. But here is some other concept called acceleration board. So that is the processing model like local aside model, right? So but for the NIC, smart NIC here, we call the type 3 is the flow through model, right? So you, in fact, the data will just go through the NIC, and after the processing or the computation, you send data back to CPU. And for the acceleration board mode, to do the machine learning is, all the data were sent to CPU first, and then offloaded to the acceleration board for processing, and then return the results back to the CPU, right? So in fact, they are different. They are not kind of type 3, as I mentioned here. So interestingly, you could find all these three types of NIC are adding more functions, right? And it is very obvious for the limitation. Okay, so the limitation are as obvious as the benefit, right? So first of all, okay, we can always add more functions or new functions to NIC, but you need to spend quite a lot of time to design, right? Even on IPGA, right? So that means you will have a quite a long time to market. And also, you know, there would be, you know, unlimited, okay, functions or requirement from the customers of or the, you know, the applications. You will not have enough resources to put all the possible, you know, functions offloaded to the NIC side. And even you will have enough, you know, resources to include the existing requirement, right? It is not cost efficient. So we would like to do it from a different angle, right? Instead of to implement all the functions independently, we would like to, okay, to group the requirement from the applications and to find some domain and to design the domain-specific programmable engines integrated into the SmartNIC. And based on that, we could, okay, use one single, you know, optimize the hardware, but to support much wider, you know, areas of applications from the software defined, you know, form, right? So just let me, okay, use an example to explain the idea, right? So here I would like to use the transportation congestion control application or as a, you know, specific domain to explain the idea. So here, okay, please just, you know, first assume this feature, right, to put the programmable congestion control is really important. There will be one slide coming soon to explain the reason why it is important, right? So now just, okay, believe me. Okay, so to do the congestion control, in fact, okay, there are quite a lot of, you know, algorithms there, but we did, after, you know, non-trivial analysis on the existing congestion control algorithms, we could form a way to abstract the processing. In fact, we could, you know, split the processing into 3 phases. The first phase is, okay, before you do anything, you need to do the measurement, or you should know the status of the network, the end-to-end, you know, network. And then based on the measurement result, you will have some, you know, algorithm, or you have some, you know, ways to calculate how I should control, you know, the rate or control the sending window, right? Then in the third phase, you will enforce the policy you just calculated from the second phase, right? So we call that the congestion control enforcement as phase 3, right? So with these 3 phases, we could further propose some, you know, programmable engines. So for example, here we do the network status detection. We further classify, you know, there are, okay, tens of metrics could be, you know, measured and be used by different kind of congestion control algorithms in the second phase. But we could, you know, group them into 2 categories, right? One is passive measurement, which usually, you know, passively collect the information and do the inference for network status. And the other one, we call it an active measurement. Usually we'll send some, you know, probes into the network, and on receiving the acknowledgement from the probe packets, you infer the network status. So in fact, we could also, you know, based on the features, we could have some domain-specific, you know, engines to do the collection of networking status. And similarly, okay, we can do or to design the programmable engines for the congestion control making phase and the congestion decision enforcement phase. One thing I would like to highlight or mention here is for the congestion, the phase 2, right? So here you may have already noticed that we have one hardware engine, which is in the block box. And we also keep the possibility to have some of the programmability still in the software, right? So this is, as I also mentioned before, we're proposing like the hardware software co-designed solution. We're not going to move from one extreme point, put everything in the software, to the other extreme point to put everything into the hardware. The principle here for us is to decide, okay, which part is most optimized, then we will make the decision, right? So this is the one point I would like to mention. Okay, so in this slide, I give the architectural diagram for the adaptable NIC prototype we have implemented. So you can see in the middle there is one green dotted line, which is used to split the system into hardware and software. So in the hardware side, on the leftmost, we have a one dashed line box, which is CMAC subsystem to handle the MAC-related functions, and followed by 4 engines I mentioned in the hardware to do the congestion control and management and the enforcement. And the third dashed line box after is the QDMA subsystem, which is handle the PCIe QDMA functions, which is also the interface between hardware and the software, right? So in fact, the CMAC subsystem and the QDMA subsystem, we can call it like adaptable, NICs shell for the NIC functions. And you could replace the programmable engines in the middle. I mean, here you can see the 4 programmable engines, PAM, PPM, PTM, PCC, right? So which I have mentioned in the last slide. So this is, flexible, architecture that you could replace with other, domain-specific programmable engines. And also you could control or program or interconnect with all these hardware functions with the, the software, which software modules, which I listed on the right. So above the driver, right? So we also need to implement a new driver. And also we need to have some, software modules in the kernel space. Here you can see the XACC, right? That is the new implementation for our prototype. And the user space functions or the software modules are mainly used for the testing and other applications. So this is the whole architecture for you to support some functions with the adaptable NIC prototype. So here, I would like to mention the story of transport congestion control. Why the transportation congestion control is important, or why we need to have one adaptive NIC to support congestion control functions. So you could see from the right bottom figure, you can see, if you are not familiar with the networking knowledge, it has been quite a long time, since 1980s, right? It has been already 40 years, but we haven't found one single congestion control to handle all the situations, right? You can see different algorithms, okay, not only for end-to-end control, but also for the intermediate control have been evolving. The reason here is we will always have, different networking scenarios or networking, infrastructure involving. For example, okay, we will have much, higher bandwidth in 1990s or 2000s, and then the past, okay, slow start is not so efficient. And then we have the mobile internet boosting. Then, okay, a loss of packet may not mean, the congestion in the middle of the network. So we need some new, congestion control algorithms. And it becomes more, and more popular in the data center or cloud computing year that we are having, more customized congestion control algorithms. There are many reasons, but I think one of the most important reasons is now the data center became a very ideal places for the, the hyperscalers, especially, for example, the cloud service vendors, to customize and to optimize their own, environment instead of without, changing or without any difficulty to interconnect still with the outside world, right? So we can see, okay, on the left, I listed many of the, attempts in the past, right, to do the congestion control customization purely in hardware, right? So I didn't mention the attempts in the software because that is, already the paradigm, right? So in the hardware side, okay, you can also do, okay, the offloading with some specific congestion control algorithm, but seems not so, agile, right? And also, we have some work just published in this year's SDI. That was a work done by Princeton. They also proposed something with very similar, motivation I just mentioned for programmable congestion control on FPGA, but their model or abstraction definitely have some limitations and cannot, provide the support for many congestion control algorithms. So that is explained, okay, the motivation here. We are doing this work. So the next question I would like to answer is, okay, then how you could, support, why I cannot, okay, there is some delay. So that's why, okay, we are here to do the infrastructure research, right? Still have some space to improve the performance. Yeah, okay. So this page is trying to answer a question, then how we could map some, okay, congestion control algorithm into the adaptable NIC. So on the left, there is one, congestion control algorithm. Most you can see the progressing is in the software side, right? And the NIC is just for forwarding packets. And now, okay, you can see all the functions in this right cycle. We could move it into, the programmable engines of our, adaptable NIC. And we still keep the function, right? The congestion control function. In fact, we split the congestion control functions into two parts. Some of them we could put into the PCC engine in the NIC hardware, and we also keep some of the, the processing in the software. So one reason, right? There are also quite a lot of reasons for us to make that design decision. One important reason is here. You probably notice, okay, on the top of, the adaptable NIC solution on the right. On the top, you could see three different, or two different, congestion control algorithms for example, cubic, timely, and we could support more. And all these different functions, more specifically, different congestion control algorithms could be, seamlessly, switched at runtime. So this is a good feature. And it is, also possible and not possible. It is also the one important feature that we don't need to, change the hardware, but we could still support new congestion control algorithms just from the software side. And we don't need to core like HLS or other compiler systems compiling, workflow to support all these functions. That means we will not, stop the running system. Everything can be done at runtime. Okay, so besides the congestion control, the congestion control algorithms, in fact, with the same adaptable NIC prototype, we could support more, applications or services. As I just mentioned, the motivation is to have, specific, Here we listed, two broad, scenarios. The one scenario we would like to use the public cloud as a user case. So in public cloud, in fact, there will be, multiple tenants sharing a single physical machine, right? So traditionally, in the cloud environment, there is one hypervisor sitting in the software to control, the bandwidth and to allocate, the resources among different tenants. But usually they are equally shared, but we could, with the help of the adaptable NIC functions, we could, offload the functions to allocate at least the bandwidth resources into the hardware. And in this way, we could have more CPU, resources to sell to more, tenants. And also, with the help of our, congestion control programmability, in fact, we could design a new function or new service for the cloud vendors, right? They could provide different tenants a new service to design or at least to select or optimize their applications from the congestion control level, right? So not necessarily to have the same congestion control algorithms for all the applications, for all the tenants, right? So another example here, I would like to say, still have some delay for me to page down. So another one is for the bare metal cloud, right? So in the bare metal cloud environment, usually the tenant or the customer would have much higher requirement for the resources. And usually they will also have not one single bare metal machine. They will have several bare metal machines to have their VPCs, right? So virtual private cloud. And in this way, we need to move the function. We need to have some management functions provided by the cloud vendor. But as I said, for the bare metal cloud, the whole machine, the entire machine will be managed or to operate completely by the tenant, right? So previously the hypervisor in the public cloud cannot be existed in the software side. So the common practice here is either put all the functions into like the switches, right? But in this solution, the access, they could only do access control, and also the scale of VPC would be limited or restricted by the size of the switch memory. And the other practice is to move all the functions into a dedicated gateway. But it is also very obvious the gateway would be the bottleneck. So we propose some, could propose some new solutions. In fact, we could move the functions from the gateway into the smart NIC or the adaptable NIC, as we said. Okay. And without changing the hardware design, based on the programmable engines we proposed, in fact, use only the programmable measurement engine. We could support many, management functions. For example, the access control, the heavy hitter detection, the port scan, threaten, many, right? Okay. Okay, so the next thing I looked at, I think, it's time for me to move from, the adaptable NIC to another place. We would like to further push, the programmability from the host network to the network core. And here, in fact, there is not too much, work in this area yet. Although we heard quite a lot of, proposals or some discussions related to in-network computing, but I would like to say it is still in a very early stage. Also, I would like to use the example, mentioned, by Bing-Shen, right? So now people would like to put, the computer or the accelerators close to data, right? That is one solution. We put, these two things together. And the other philosophy behind this adaptable switch is, where we could do from another angle, right? We could compute or to the processing on the way during you transferring your data, right? For example, you could do some calculation, before the data arrived to another remote, server, right? And that could be done in switch, right? So in fact, to make it happen, in fact, we could have two, we will have two different, we will have two steps. The first step, we would start from a simple, or not simple, but more straightforward way, right? We will have two chip approach, combine switching ASIC and a cap node, right? And we would like to use the flow-through processing. And in the second step, in fact, we could integrate the functions together into one single chip, right? And in that way, we could also use the local site processing architecture. And in all these two steps, we will integrate the software stacks together. Okay. And we have done some preliminary work to provide. Yeah. So yeah, I'm waiting for the next slide coming out. Okay. So this is the architectural diagram of an adaptable switch we proposed. In fact, there are two subsystems. As you can see, the left big box is the fixed function of switching system. And the right-hand side is the programmable logic system. We could simply use FPGA or ACAP or other kind of MPSLC, right? In the left side hand, we need to have some modification on the traditional switching chip. We will integrate some programmable engines here. Similarly, like previously I mentioned for the adaptable NIC. So here I listed like the parser, the matching action. In fact, that we could use the SDNet toolchain, right? Still propose the programmability. Although we call it the fixed function switching subsystem, but we could still have the programmability there. And mainly on the SDNet, mainly on the programmability for the networking stacks. And also you can see we will have the MMU system, which is to, for the management of the memories here. The reason we put such a module or function here is, okay, we would like to solve the problem or solve the bottleneck between the two subsystems. No matter it is one chip solution or two chip solution, right? So we need to interconnect the switching system and the programmable logic system. So based on the real trace, right, there is not necessary for us to transfer all the data, from the switching system to the programmable logic system. Usually, only a small portion of the traffic need to be processed by some customized logic. And also even you need to process with some customized logic in the switch, right? You only need to look into the headers or a small part, a couple of bytes, right, in the payload. So that is the reason we would like to propose in the second step for the local side model, which could solve the problem of the bottleneck in the interface between these two subsystems. And we also would like to mention some user cases here, right? So we implemented 3 kinds of user cases based on the design I just mentioned for the adaptable switch. The first one is event-driven processing. This is to solve the limitation for the existing programmable networking devices like P4 or SDN, right? So which could only trigger the customized processing either on arrival of a packet or on the leaving of a packet. In fact, okay, we could trigger the processing on some specific moment. For example, here to the congestion control, you could keep track on the buffer occupancy, right? So and similarly, we did other 2 user cases. One is firewall to provide stateful processing, which is also a restriction for P4, and also algorithmic capacities, which is also not so not rich enough from the P4 community. And the key here is to how to design similarly the programmable agents, and how to make it split it into different process pipelines, and I think they are quite similar, like previous the past 2 partitions, right? Also need to split the data and the processing engines, and also we need to have several different engines may have conflicts on data, so we need to solve the problems there. And also more importantly is the the development flow. So due to time limitation, I will not go to the details of them, but I just would like to share the result here. We could see with our preliminary prototype, we could provide a couple of terabytes for processing to support it is usually enough for the processing in a switch. Okay, so to make it a more much wider application scenarios, we could also think about integrating the in-network computing here. So there are a lot of very popularly or widely used software processing framework nowadays. Right? I just have one example here, like Kafka, right? So learn from the architectural figure here, the Kafka cluster in the middle were as just like a switch, right, to exchange the data from the data producer and data consumers. But in fact, we could also use a switch in the middle to do the functions like Kafka cluster, and to reduce the the chance for a much longer transmission of the data, which will have much better latency performance. So this is still undergoing. We don't have any results for this, but yeah, this is I think would be a very promising direction in the future. Okay, as a summary, we propose the distributed adaptive computing, and this is the motivation here is to not only to accelerate a single node, but we do the optimization of the design in the context of a distributed manner. Another important idea behind is we don't want to integrate or add independent functions separately to no matter either the NIC site, NIC place or switch places. We would like to have domain-specific programmable engines into these networking places to do the acceleration of the performance optimization. And the second one I mentioned, okay, quite a lot of user cases, right? Just to showcase the value of the programmable engines or the adaptable NIC and the adaptable switch, right? Also with the goal here is trying to achieve at the same time for the flexibility and the performance accelerated from the hardware side. And last, I would like to mention that, okay, we had quite a lot of discussions with hyperscalers. So although currently we don't have too very deeper discussion on the adaptable switch, but we did get very positive feedback from hyperscalers related to our adaptable NIC idea. So this is okay. I think everything I would like to talk today. And let me give it back to Bingshen. Thank you all.
Thanks